This is the chapter 12, first lecture, first notes for the changes of state and states of matter. So first thing is that, of course, the states of matter are plasma, gas, liquid, and solid. We're not going to discuss plasma a whole lot. In a lot of ways, it's very similar to gases. But they do start with gases in the chapter, and that's where we're going to start. The beginning, one of the first things that you should be able to do is to state and discuss the kinetic theory, and they call it kinetic molecular theory. There are two main parts, and that is that the gases are composed of tiny hard spheres that are, of course, gases are mostly space, and these spheres are in constant, straight line, and random motion, and when they have collisions, the collisions are perfectly elastic. What perfectly elastic means is that when they collide, they separate and they haven't lost any energy. On big scale, like when you play pool and you hit the cue ball, eventually the balls stop rolling because of all the frictions and air resistance. On the small scale, these particles, remember, they are the air. So there's nothing around them that's going to slow them down. And when they collide, say if we had something with 4 joules and 6 joules, when they left, they might be 5 and 5, but they're still going to add up to the same total energy. So that's what perfectly elastic collisions would mean. And gases in the cylinders, like the ones I have here in the lab, they've been gases. Some of the cylinders I haven't filled for 12 years. They're still gas, which means that the gases are colliding inside thousands of times a second, and they are still colliding today. They haven't collided and lost their energy and dropped to the bottom as liquids. So when we talk about the gases, one of the things you need to understand is we're going to discuss kinetic energy. Kinetic energy is the energy of motion. So when particles hit and collide and move, that's kinetic energy because they're moving. Our formula for kinetic energy, if you look at your notes, I've got it up on the screen also. It's probably a little easier if you've got your hard copy for the notes. Ke equals 1/2 mv squared. And that means that kinetic energy equals mass times velocity, 1/2 mass velocity squared. So we're really looking at mass and velocity. So what we have happening, we've got a big molecule. We'll let this book represent the big molecule and the little molecule. The little molecule moves a lot faster, the big molecule not so much. And the reason, think of an example of a car. The big molecule would be like the car, and this would be like the bicycle. The same amount of energy, we have the same energy in the big book and the little particle, means that the little molecule is going to move faster because it's smaller. And remember, it's m times v. So when m is big, v is small. When v is big, m is small. And that's true for all the gases. So when they're all the same temperature, a big gas is going to be moving slower, a small gas is moving faster. There's a law, and we're going to talk about 2 of the gas laws in this chapter, that relates that idea of speed and mass, and that is Graham's law. And Graham's law, and on the notes, it's rate of A over rate of B. I like to say rate of small over rate of B for big equals, and notice that it is flipped, that the small is on top on the left and the molecular mass of the small is on bottom on the right and the big is on top, because what we want to do is we're comparing the rate of a small gas to a big gas. It's going to be a number bigger than 1 because small gases move faster. So it's not going to be the same speed, which would be 1. It'll be 2 times or 3 times or 4 times as big. And that's why the molecular mass of the big one's on top, because we're going to get a number greater than 1. Where do we get the molecular mass? You look at the periodic table. Okay, so we're looking at a practice problem on the next page that says, let's compare hydrogen and oxygen. So the small is going to be H2, and the big is going to be O2. Well, over here on the other side, we're going to put the molecular mass of the big. We look at the chart. We see oxygen is 16, but it's O2. So that's going to be 32.0 grams. And the molecular mass of the small one, of course, hydrogen, if you look at the periodic table, the number at the bottom is 1.0, but it's H2. Remember, these are both diatomic. So that's going to be 2.0 grams. Well, the easiest way to do this, you can separate it and do the square root of that, divided by the square root of that. Mathematically, it's the same either way. It's easier in this case to divide 32 by 2, which is 16, and then we do the square root of 16, which everybody knows is 4. 4 times 4 is 16. Square root of 16 is 4. What does all this mean? Well, we translate this by saying that the rate of hydrogen compared to the rate of oxygen, hydrogen's 4 times as fast. And as far as significant digits, we've got 2 significant digits, so it'd be 4.0 times as fast. That's Graham's law. So when we talk about gas pressure, onto the third slide, pressure is defined as the force exerted per unit of area. So area is going to be in square units, like inches squared or meters squared or centimeters squared. When we talk specifically about air, well, then it is air pressure or atmospheric pressure. And we use a barometer to measure air pressure. If you were to walk outside and maybe draw a little square-inch square on your skin, the column of air that is from your arm all the way up to space would be about 14.7 pounds. And we call that 14.7 pounds per square inch. That is one way that we can report pressure. One way we do here in the United States. Other countries use different units because other countries use the metric system. We don't, at least except for scientists. So what that means, 1 square inch all the way up to space, that column of air would weigh 14.7 pounds. When you put air in your tire, we use PSI there. It's usually 30, 35, 40 pounds per square inch. So that's one of our ways of reporting. Notice that on this third slide, we've got 14.7 psi equals 760 millimeters of mercury, equals 101.3 kilopascals, equals 760 torcellis. Those are all units that we use. And, of course, it's kind of like 1 foot equals 12 inches, okay, or 1 centimeter equals 2.5. I'm sorry, 1 inch equals 2.54 centimeters. It's just equivalent measures. We could use these to do dimensional analysis. And that's a large part of the math that we do in this chapter, like we did in some of the chapters last semester. I think the dimensional analysis in this chapter is a lot easier than those. It's all 2-step and fairly easy 2-step problems. So we're going to look at these units a little closer. Why or how do we get the 29.92 inches of mercury or the 760 millimeters of mercury? Where do we get that? Well, we use a meter stick that, let's refer to the meter stick. It's got metric on one side, inches on the other, and a mercury barometer. So you can see up here, this is a model, and it's not to scale. It should be bigger and taller if we had a real one. That's what a mercury barometer is. We don't use those much anymore because mercury is such a hazard. But basically, you take a tube, a glass tube that's sealed on the bottom, fill it with mercury, and then you invert that into a dish. And mercury is very heavy, so you'd have to get some help, putting that upright, otherwise the glass tube would break. And up the top, the mercury was originally all the way at the bottom of the tube, so when you turn it over, that's a vacuum. And the vacuum pulls mercury up the tube. But when you have pressure pushing down on the dish, that forces mercury up the tube. When you have a low pressure, the column is low. When you have high pressure, the column's high. We measure the height of the column. That's where we get the units of 29.92 inches of mercury. We put the 0 in down on the bottom, down where the at the level of the mercury in the dish, and we measure how high the column is. And if we look at the 29.92, which is right here, and flip over the ruler, lo and behold, that's exactly 760 millimeters of mercury. So it's just the two systems, the English system and the metric system. That's the way that we measure. Now, notice that the 760 millimeters of mercury is also equal to 1 ATM, 1 atmosphere. That's another unit that we use. And we also have another couple of ways we refer to the millimeters of mercury. Millimeters of mercury can also be called millibars. Same number, same value, 760 millibars. And there's also 760 torrs, T-O-R-R, which is torricellis. Same unit, it just has a name. It's named after a chemist that did some experimentation with pressure. So this device is called a barometer. You need to know that that's how we measure air pressure. More units of pressure. So on this page you can see that we've got really all of the units now. 1 atmosphere, 760 millimeters of mercury, 29.92 inches of mercury, 14.7 psi, and of course the 3 units that are basically the different names for the 760 millimeters of mercury, 760 torrs, 760 millibars. So those are all used, and we'll use those to do calculations. Like a barometer measures atmospheric pressure, a manometer also, and it's a curved tube, but when we have a sealed container, we hook a manometer to it, and the more evaporation or vaporization that takes place, the more vapor in the closed container pushes the liquid around on the manometer, and that causes it to go up, and it's a way that we can measure pressure in a sealed container. That would be manometer. So talking about math with pressure units, you know, this really, at this point, I could say use dimensional analysis, and that's it. We're done. We really don't have to go into it any further. I am going to go through an example just so we kind of refresh our memory about dimensional analysis. So for the example, the first example, our known is 788 millimeters of mercury. Our unknown is how many ATMs. So, like we did before, draw 2 blanks, an equal and a third blank, and your known is going to go into the first blank, so 788 millimeters of mercury over 1. We're going to put our unknown units, ATM and ATM, over here, so that we have the unknown units in the last 2 blanks, and we're going to cover the number on the first blank, drag the units down, millimeters of mercury, and now we just go to our the previous page, and we're going to put the units that we saw on the previous page. 1 atmosphere equals 760 millimeters of mercury. Now, these are both whole number conversion factors. They don't affect our significant digits. When we multiply 788 times 1 divided by 760, you can see on the next screen that we get our answer, 1.036842 atmospheres. Because we've got 3 significant digits, we rounded to 1.04. That's our answer. We've got our units. We've rounded it correctly. And there's another example problem for kilopascals there also. And we use kilopascals. Pascal is a really small unit, so it's kind of like meter. When we measure between cities, we don't talk about how many meters a city is away. It's how many kilometers when we're using the metric system. So kilometers, kilometers, kilopascals as opposed to pascals. So we're going to talk about our second gas law that's mentioned in this chapter, and that is Dalton's law. Dalton's law is probably the easiest of the gas laws, because Dalton's law is basically just Dalton's law of partial pressures. Just says that in a container or in a space, the total pressure is the addition of all the partial pressures. So if we have more than one gas, then you just add up their pressures, and that tells you the total pressure in the space. An example we have down here, CO2 has a pressure of 0.55 atmospheres in a container, and O2 has 0.75. What's the total pressure? Well, it's just the pressure of the two added together. When you add 0.55 plus 0.75, we get 1.30 atmospheres. And that's it. You just add the parts. The parts equal the total pressure. That's Dalton's law. Now, I would like for you to know the names of the two laws, Graham's law and which law it is, Dalton's law. I will put those laws on the possibly useful page, but I'm not going to name them. You need to know which one has which name. All right, so we move on and talk about intramolecular attractions. Just a review about chapters 10 and 11. If you remember about ionic and molecular compounds, our two types of intra would mean inside of a molecule. Molecular connections would be ionic, and molecular or covalent bonding. We're also going to talk about intermolecular, which means between two molecules. So like two separate waters, what makes those two waters stick together? There's a mention again about metallic bonds. Just to remind you about metallic bonds, works a lot like ionic in that you've got plus ions. Metals lose their electrons because they're mobile, and they become positive ions. So if we had something like sodium, Na, it's not going to exist as Na, it's going to exist as Na plus, because the electrons are jumping around like fleas on a dog. And the electrons jump between the two Na pluses and help lock them together. So much like plus minus when you have an ionic compound. So move on. The forces between molecules, this is what we call like interstate highway goes between multiple states, international talks between Mexico and the United States. So these intermolecular forces, to review, because we've done those, dispersion forces, dipole, hydrogen bonding, these are in molecular compounds. And of course, in an ionic compound, it's a little bit confusing because the intramolecular, what holds together Na plus and Cl minus, is an ionic bond, but the plus minus also holds other NaCl's, so it's kind of like the ionic bonding is like three-dimensionally, and that's what makes the lattice or the crystals that we built back when we did chapter 10. So in order, dispersion forces, which is just moving electrons, make a magnetic field. The magnetic field attracts two molecules, and it's the weakest force. Things like methane, CH4, are a gas because they don't have the other forces, but they have a little bit of an attractive force. When they hit, they bounce right off because it's not enough to keep them together. Unless we cool the gas to really low temperature, then when they hit, those forces are enough to keep them together because there's not very much energy, and they become liquid and drop to the bottom of the container. Dipole attractions. This is the second strongest. And then hydrogen bonding is a special type of dipole. It's like in water, you have hydrogen is positive and oxygen's minus. That's what makes all the special things happen in water, that the surface tension and the fact that it's liquid when almost all other molecular compounds the same size are not liquid, they're gas. Of course, ionic compounds, they're all solid at room temperature because of the tremendous attraction between formula units. Properties of compounds and metals in general, when we talk about the properties of compounds, molecular compounds are liquids or gases because they don't have tremendous attractions between molecules. And very few of them are solid. The really big molecules are solid because now they also have lots of dispersion forces because lots of electrons. The bigger a molecule is, generally the higher its melting and boiling point. And so ionic compounds are almost all solid, have very high melting and boiling points. Molecular, very low. And of course, metals have high boiling points and melting points because they're a lot like ionic compounds. They're attracted by plus minus attractions, and that keeps them together. So that's it for the first notes on chapter A. Beyond that, if we, if you look over your practice foldable. That would be a good source of how to solve problems with the dimensional analysis. We'll finish up on Notes B. We'll finish up the rest of the chapter and practice, work on your review, and we will see you then.